In this video, we're going to be designing a launch vehicle flight control system using MATLAB and Simulink, and then performing a simulation in FlightGear. This video will look into control design methods using state space and LQR. So what is a launch vehicle control system? It is simply a method and an algorithm for a rocket or missile to achieve its mission trajectory and also to control it during takeoff and landing. Obviously, rockets are very powerful and they have a lot of force, so controlling the vehicle and making sure that the vehicle stays stable during flight is very important. Rockets also use their control system to release a satellite into orbit and to also land. And why should we design it in using MATLAB and Simulink? Well, MATLAB and Simulink are the go-to software in the control system industry, especially today, because they're very robust and they can be used for multiple applications. Also, NASA and SpaceX do use control in MATLAB and Simulink to design their rockets, for example, the SLS Space Launch System, and also the landing of the Falcon Heavy and the Falcon 9 rockets. So for our problem, we will be controlling a rocket during a takeoff phase or the ascent phase, because this is when the launch vehicle is quite unstable and it has to clear the atmosphere safely. For this case, we'll be using the control input as the gimbal angle or the force at the bottom of the rocket generated by the nozzle and the engine, and the outputs will be the pitch angle, the pitch rate or the angular body rate, and the drift. So drift is something during takeoff which occurs in rockets because of wind, and it's basically the rocket moving sideways. Now, drift is an addition to the z velocity. So for example, if the rocket is taking off like this, drift will just push it more towards that axis, so it'll keep moving down. If you want to look at how the rocket is derived and how the equations of motion are made, you do need to look at the paper and the blog post link in the description below, because this is where it shows all the constant values. And I won't be showing it here because it'll just be a repeat. So I'm going to be going straight into the problem now, and let's get started. So guys, we can start building the model, and you open the new file and write CLC semicolon close all clear all. This will allow you to clear the memory every time you run a new MATLAB code, so it'll save a lot of space. Next, you can input all the constant values. So in this case, I have them pasted into Notepad. And once again, look at the paper below to get these numbers. Just paste them in there, and then you can also do the same with the other constant values. When they're all pasted, you can build the state space model, but I'm just going to first put comments on them just so that we can refer to it and we can change things if we need to. So for the state space model, it's simple. Just write your matrices. A underscore M is the aim matrix. I have 0, 1, 0, M alpha, 0, M alpha over V, and then do the last row in a similar manner and put a colon at the ending, because that's done. Next, you have B underscore M for the B matrix. It'll just be 0 M delta TC over M. C matrix will just be a diagonal of ones because we just have our states there and we don't have any feed forward, and this means that the D matrix will be 0 because the D matrix corresponds to the feed forward matrix. Next, you can build the state space model by just typing in SS brackets A underscore M comma B, comma C, comma D. So that this will make the state space model from your A, B, C, and D matrices. You can save this now. I have it saved as state underscore space, and it'll be an M file. We can quickly run this and see what it looks like. It's giving us an error, which means that the M alpha is actually N underscore alpha. So we can quickly fix that. And then when you run it again, you have the model there. So guys, here are some basics on LQR. It is basically a method to minimize the work done by the controller on the system, and it accomplishes this by using a cost function and a weight matrix. Looking back at our state space representation, you have x dot equals ax plus bu, where x is the state of the system. So for this case, it'll be the pitch angle, the pitch rate, and the drift. U is the input, which is the TVC angle. The LQR algorithm is j equals half multiplied by an integral of a function of q and r plus half of a function of p. This full equation is in the link below, so please take a look at that. Q is the cost matrix, r is the weight matrix, and the feedback law is given by u equals kx, where k is the feedback gain, which is obtained from the LQR method. Next, we can build the LQR model or the cost function model. But first, let's write the vectors. So C vector is B, O, R, O, and G, O, just to break up the cost vector. Then we have the R vector, which is the weights, as I explained before. So in this case, we're putting minimum weight on the pitch angle because we don't want to minimize that. And we're putting maximum weight on the drift. So the lowest weight is the TBC angle and maximum is the drift. So let's make a for loop for k equals 1 to 1. You have your R matrix drift, which is the drift matrix. Then you have the Q matrix, which is the cost matrix. So it'll be 1, 0, 1 over V, semicolon 0, 0, 0, and 1 over V, 0, and 1 over V squared. This is because the cost is the drift and we are trying to apply to that. This matrix is shown in the blog post, so look at that if you don't understand how it occurs. Next, you have the LQR code from the MATLAB. So it'll be K, S, and E equals LQR pitch. So the pitch state space matrix, so pitch underscore SS as we wrote in the first script. Then you have Q and R. This is the standard MATLAB command for LQR, and it'll be included also in the MATLAB documentation. So you can also find it over there if you're confused. Next, you have another loop because now we're trying to plot the eigenvalues and see what the stability of the system is. In control design, it is always important to look at how stable your system is because you can change parameters based on that, and you also want system performance to not be compromised while it's operating. So in this case, we have eigenvalues of A minus BK, and we're trying to normalize it, so we're dividing it by 10,000, and we're doing a whole bunch of iterations there. So when that's done, you can also create a plot of the real values and the imaginary values. If you guys know anything about complex numbers, they have a real and an imaginary section. So that's what I'm doing here basically. We're just trying to plot the root locus because that's a combination of the real and the imaginary values. And then I have that C vector which I wrote before because just to label it. And just copy and paste this twice, and then let's do it for all the states because it is a vector, so we need to do that here again. And write grid so you can show the grid. Next, you can just do some graph stuff. So let's label the X limit points, and let's also write a legend R equals 0.1 because that's what we chose for the pitch angle. Save this as cost underscore function, which will also be an M file. And if you run this, you can see the R vector is showing there, so that's good. And then you will see the root locus graph. So it is quite stable. Or actually, I would say it is marginally stable, and part of it is unstable because we have some values which are in the positive plane. So then we can assign the feedback gains. So that's the K matrix as I mentioned before, and it'll just be like K1, K2, and so on. So those will be your LQR gains, and they're obtained below here. So just to show you guys what happens when you run both these scripts, if you go into the MATLAB workspace, you will see that they all show up. And this is crucial because when we actually go into Simulink, Simulink will pull values from the MATLAB workspace, and this is very important. You can actually assign variables in Simulink because if they are defined in the MATLAB workspace, Simulink will know that it's there and it'll just pull the constant value from there. You can see how when I run these two codes in C sequential format, the second code is actually based on the first code because we have the state space matrix defined there. And when you run this, you'll see that the workspace gets populated with all the variables. So this means that all the variables are now defined and we can use these exact values in Simulink. So let's open the Simulink and let's start modeling our simulation. The first thing you can do is save your model. I have it saved as a .slx file and I called it LQR_control. Next, you can drag in a constant and rename that as your TBC angle, which is your input of 0.01. Next, you can drag in a sum block and change the sign to minus because this will be your feedback gain. When that's done, you can drag in a multiplexer to combine signals, but this is actually a demultiplexer because we need to break the signals up first. And the reason for this is because we need to apply our LQR gain. So drag in a bunch of gain blocks and this will be your K, so it'll be K1, K2, and so on. And you double click on the block and you can assign the variable. So this is what I said before, Simulink can pull values from the MATLAB workspace. So if you define the variable like that, it works. So just do K1, K2, and so on. When that's done, you can drag in an addition block and change the signs appropriately, because when you multiply matrices, if you recall, the control input is u equals kx. So when you multiply matrices, you will add the values up. So you need to do that. Next, you can drag in the state space. Now this state space is the rocket itself, and going to the matrices and type in the matrix name. So A underscore M, which we had before, B underscore M, C and D, so on. And for the initial conditions, type in 0.200 because we don't have any initial drift and angular rotation. We just have an initial TBC angle, or the pitch angle for this case. So it'll be 0.2. When that's done, you have a simple control system, as you can see here, but we can break up the outputs. But first we can make a subsystem. As you can see, you just click and drag and then adjust it. A subsystem helps you make the code look a lot more neat, and you can also change the inputs and the outputs much faster. When that's done, let's drag in a demultiplexer to break up the outputs, because all the outputs are in the same signal, but if you want to take a look at each output, it's better to break it up. And we can finally drag in a scope. So when we run it, we have an error because the matrix is undefined, and as you all know, the reason why it's because we didn't run the MATLAB stuff yet. So going to the same folder, and another thing to make sure is that all the files should be saved in the same location. So run state space first because you have to activate that, then cost function, that'll be a graph, and when that's done, now we can go into Simulink and run it. So we have a simple output there. As you can see, the angular rate, it jumped and then it went back to 0, so that's good. You know, you don't want the rocket spinning too much, right? So you want to keep that at 0 as much as possible. Let's drag in the scope and let's take a look at the angle itself. So the angle first goes down a bit because we have a TBC input, and then it'll stabilize, right? Because when you change the gimbal angle of the rocket will turn and then it'll just stop moving. Also taking a look at the drift, because we do have wind and things like that, and also uncertainty in the system. You will have drift for sure initially, because also you have Z motion, right? Because the pitch angle is non-zero. So this is our basic system, but we can actually move on and do more stuff. We can actually create a full-up flight simulation of our rocket, and to do this you have to first look at the equations of motion. And when you have that, you can let's drag in sine for the T sign, but now we're changing it to cosine here. So we just need the pitch angle now to build the simulation. T cos alpha, T sine alpha. If you draw a free body diagram, you can just simply draw lines and connect it like that. So that's your force, and our force was defined in the problem, but in this case I'm downscaling it, and the reason is because in FlightGear, when I do the simulation, I don't want the rocket moving too fast, so I'm basically slowing it down manually by using a smaller value. So you can multiply the things and you can drag a product block. So this is simply T cosine of alpha, or the pitch angle in this case, and do the same thing for T sine alpha. Change the function to sine and drag in the same force. You can make it look very neat like this. So now we have the motion of the rocket, and this will allow us to build the simulation. But there's actually something else we are missing. We need to account for the drift, because we do have drift of the vehicle. So what you do is you need to break the drift into Z, right? We have Z dot, we have a drift rate, and we need to make it into Z. So to do that, you have to drag in an integration block, because you have Z initial and it'll be added onto it. So the T sine plus the drift gives you the total motion in that axis. And I'm dragging in a different integrator because I need to know what the Z is, right? So that's what I'm doing here. Next, you can add them both up, and then you can once again drag in an integrator to get the height. So you have H dot to height. So I'm dragging these both now, and I'm making a display. So you can see the height, rate, and the drift change. Now you can also integrate this more and get the actual position. And the way I did this, connected this into FlightGear, was simply I used a FlightGear block, and you can see how it is done here. I just used my video on how to connect MATLAB to FlightGear. I do recommend you watch that. because this talks about this stuff in detail, the blocks you need, and you will need the aerospace block set for this. So I do strongly recommend that you watch that as well if you want to build your own launch vehicle simulation. So that is our final simulation, and it'll look like this. My name is Vinayak, and I'm the creator of Video Engineering. I'd like to thank you all for watching this video, and if you do have any confusions, keep in mind that this work is not originally mine. The simulation stuff was mine, however, the actual control design was done by someone else, and it's shown in the paper in the description below. Because the thing is that in launch vehicle control design, there's many ways to build the actual controller, and this was just one example. There's many more. So all the links are in the description below, and you can also download my Simulink Model for reference checks. With that being said, thank you for watching, and I'll see you guys in the next video. Take care, bye-bye.